YouTube, what's up? Everything Engineering here. Today we are doing a video on finite element methods again, and we're going to be finding the internal forces of our spring system here using our stiffness matrix that we derived in a previous video. So looking at this example is the same example that I derived the equations for in a previous video, and I'll link it here so you can get a better picture of where some values came from. So all of this is given here. We got 4 nodes, 1, 2, 3, 4, so that gives us 4 degrees of freedom. And we have 3 different elements, 3 different springs. K1 equals 100 newtons over 1 meter, K2 equals 100 as well, and K3 equals 200. And we've got an external applied force of 20 kilonewtons at node number 2, and node number 3 is nothing, and at nodes 1 and 4 we've got fixed end supports. So if we remember what fixed end supports mean, that means our U1 is 0 and U4 equals 0 because they're fixed and no movement will occur. And now we know that there will be a U2 and there will be movement at node number 3. Okay, so now if we want to break this up, so I'm going to show you guys how to solve for the internal forces. My previous video we solved for the external reaction forces at nodes 1 and 4, and as well as the displacements at nodes 2 and 3. So if we look down here, we have our system, our spring system, broken up, and let's start labeling some stuff. So we got a 20 kilonewton force, and if we go to node number 4, we're going to have our reaction force F4, and also F1 reaction force. Okay, so now that we've labeled these reaction forces and say that we've solved for these reaction forces, this 20 kilonewtons now doesn't really have any factor, any role in solving for the internal forces of each individual spring. Now it's just a function of our K and our displacement. So if we start over at node number 1, we're going to have a reaction force, or sorry, we're going to have a internal force going in the positive x direction due to the reaction force at 1. And this is denoted as F, 1x, and 1 in brackets. So this means that the internal force at node number 1, that's what the first little subscript means, node 1, due to element 1. So you'll see this annotation in the textbook. So this means the internal force is lowercase f at node number 1, subscript 1, and then in brackets on the top superscript 1, meaning due to element 1, because if we remember, this is our first element, second element, and third element. So this is K1, element 1, so the little force internally due to the first element. And then these, to be in equilibrium, have to be equal, right? And then switching over now to node 2, so if we don't look at this 20 kilonewton force, just worry right now about labeling properly our internal forces. So this needs to be in equilibrium, so we're going to have a force this way and a force this way to keep everything balanced. Okay, and now these are just annotations. When we do the matrix, all of the signs, if everything's labeled correctly, will work out, but this is just for kind of a description purposes for you to understand where everything's coming from and where my labels are coming from. So now we're looking at our internal forces at the second node, right? So F2x, and now it's still 1 because it's due to the first element, and that is this guy. Okay, and now we need to look at this force on this end of the node. So we'll just still annotate this as lowercase f, so the internal force at the second node, but now we're looking at the second spring. So in brackets, superscript is going to be a 2, okay? And those are going to be equal and opposite signs. And similarly, it's going to be the same thing at node number 3. 3x, so our internal force at node 3 due to member 2, okay? And now internal force at node 3 due to member 3. And finally, our internal force at node 4 due to member 3. Okay, so now we know this. We can solve for our reaction forces, and we can solve for all of our displacements. So this is important to know, the annotation for the external forces versus the internal forces, okay? So now we're going to set up our matrices just like we did in a previous video. The previous video solved for our stiffness matrices, and I'm just going to write them out. I'm not going to bother solving them because you can click back, watch the video, and find out how I got those. So, okay, so here's our 3 stiffness matrices. K1, K2, K3. And now for the first member, the first element here, the first spring with our constant 1, we have 2 nodes, right? We have our 1 node and our 2 node, right? So putting this into matrix form, if we recall that the force vector is equal to our spring constant K matrix times our displacement vector, right? So putting all of these individual matrices into this form, we're going to have 3 sets of matrices, giving us, for the first element, we have 2 nodes, right? We have node 1 and node 2, so therefore we're going to have an internal force at node 1 due to member 1, and an internal force at node 2 due to, and an internal force at node 2 due to member 1 as well, because we have this one that I'm circling, and then we also have this force. These are both acting on our first spring. So we're going to have a matrix that corresponds with this system.